A teaspoon of a neutron star weighs 6 billion tons. That is roughly the combined mass of every human being who has ever lived, compressed into a volume smaller than a sugar cube. If an object that dense drifted within 1 million kilometers of Earth, the planet would not shatter on impact. It would not need to. It would stretch, slowly at first, then catastrophically, pulled like taffy into a spiraling ribbon of molten rock long before the two objects ever touched. But here is what nobody asks. Why stretching? Why does the planet not just fall straight in? The answer reveals one of the most elegant and violent principles in all of physics. Gravity gets stronger the closer you get to a massive object. That much is familiar. But the key is not the strength of gravity, it is how rapidly that strength changes across a short distance. That rate of change is called a tidal gradient. Around the Sun, the tidal gradient across something the size of Earth is gentle, enough to raise ocean tides, nothing dramatic. But a neutron star packs more mass than the Sun into a sphere roughly 20 kilometers across, about the width of a mid-sized city. That means the near side of any object close to it feels enormously stronger gravity than the far side. The object does not fall uniformly, it gets pulled apart, stretched along one axis, compressed along the others. Physicists call this spaghettification, and it is the single principle that explains every phenomenon in this video. Extreme density creates extreme tidal gradients, and extreme tidal gradients destroy everything they touch. So picture the scenario. A rogue neutron star, gravitationally unbound to any system, enters our solar neighborhood. This is not pure fantasy. There are an estimated 1 billion neutron stars in the Milky Way alone, most of them dark and drifting, no longer emitting enough radiation to detect. They are stellar corpses, the collapsed cores of massive stars that exhausted their fuel and had their outer layers blown away in supernovae. A typical one carries about 1.4 times the mass of the Sun, packed into that 20-kilometer sphere. At a distance of 1 light-year, roughly the outer boundary of the Oort cloud, a neutron star's gravitational influence would begin nudging comets and ice bodies out of their long, stable orbits. Nothing dramatic, no visible change in the night sky, but gravitational perturbations would ripple inward over centuries, slowly destabilizing the delicate resonances that keep the outer solar system organized. The first real consequences arrive once the neutron star passes within a few hundred astronomical units, still far beyond Neptune. At this range, its gravity begins competing with the Sun's for control of the outer planets. Orbital resonances break. Neptune and Uranus might be flung out of the solar system entirely or dragged into chaotic new trajectories. The timescale here is still thousands of years, long enough that no human lifetime would register the change, but unmistakable in astronomical records. Now compress the timeline. The neutron star crosses inside Saturn's orbit, roughly 10 astronomical units from Earth. Something remarkable happens. Tidal effects on the Sun itself become measurable. The Sun is a sphere of plasma held together by its own gravity, and a tidal gradient from a neutron star at 10 AU, subtle but real, deforms its shape ever so slightly. Solar activity could turn erratic, but the Sun holds together. Not yet. Here is where the mathematics turn vicious. Tidal force scales as 1 over the cube of distance, not the square. That cubic relationship means halving the distance does not double the tidal force, it multiplies it by 8. Halve it again, 64 times stronger. This is why approach scenarios accelerate so rapidly from inconvenient to apocalyptic. At 1 astronomical unit, roughly Earth's distance from the Sun, the planet's orbit is no longer stable. Earth spirals inward or outward depending on exact geometry, and the tidal stress on the crust becomes immense. Earthquakes of a magnitude never recorded. The ocean is not just raised, it is displaced entirely, sloshing across continents in walls of water hundreds of meters high. The atmosphere itself begins to distort, pulled preferentially toward the approaching intruder. But the true destruction begins inside the Roche limit, the critical distance at which tidal forces overcome an object's self-gravity. For Earth approaching a 1.4 solar mass neutron star, that boundary sits roughly 12,000 kilometers from the neutron star's center. Inside it, Earth's gravity cannot hold the planet together. The disintegration is not an explosion, it is an elongation. The near side accelerates toward the neutron star faster than the far side, and that differential stretches the planet into a long, thin stream of debris. Rock, iron, ocean, atmosphere, all drawn into a glowing accretion stream spiraling around the neutron star, heated to millions of degrees through friction and compression. From a distance, it would look like a luminous thread wrapping around a point of intense gravity, brief, beautiful, and total. The Roche limit is itself an elegant consequence of the tidal gradient principle. Every gravitationally bound object is held together partly by self-gravity. The Roche limit is simply the distance where the external tidal gradient exceeds that internal binding. For a fluid body, the classical formula puts it at about 2.4 times the radius of the more massive object. A neutron star has a radius of roughly 10 kilometers. Multiply by 2.4 and the fluid Roche limit sits only about 24 kilometers from center, barely 14 kilometers above the surface. But Earth is not a fluid. Chemical bonds in rock are vastly stronger than gravitational self-binding at planetary scales. The real breakup distance, accounting for material strength, is several thousand kilometers, still terrifyingly close, but far enough to matter. This gap between the fluid and rigid Roche limits is exactly what determines whether a moon survives a close orbit or becomes a ring system. The same physics that would hypothetically shred Earth is what gave Saturn its rings, from moons that drifted just slightly too close. That is what tidal gradients do to a planet from a distance. But this principle was not first understood through a hypothetical catastrophe. It was discovered through one of the most elegant accidents in the history of astronomy. In 1967, a graduate student named Jocelyn Bell Burnell was analyzing data from a new radio telescope at Cambridge. The instrument was designed to study quasars. But buried in the data, Bell Burnell noticed something unexpected: a regular pulse of radio waves arriving every 1.337 seconds with precision rivaling an atomic clock. The regularity was so perfect that the research team half-jokingly labeled the source LGM1, Little Green Men. Nothing natural, they assumed, could pulse with such clockwork precision. But within months, Bell Burnell found 3 more pulsating sources in completely different parts of the sky. 4 separate alien civilizations, all broadcasting at slightly different frequencies? The simpler explanation won: these were natural objects. But what kind of natural object could produce such mechanical regularity? The answer had been predicted 33 years earlier. In 1934, astronomers Fritz Zwicky and Walter Baade proposed that when massive stars collapse at the end of their lives, they could form objects composed entirely of neutrons, matter compressed so tightly that electrons merge with protons, creating a sphere of pure nuclear material. The idea was so extreme that most physicists ignored it for decades. Bell Burnell's pulsars were exactly what Baade and Zwicky had described: a neutron star, spinning rapidly, emitting beams of radio waves from its magnetic poles, sweeping those beams across the sky like a lighthouse. Each time a beam crossed Earth's line of sight, a pulse. And some neutron stars spin hundreds of times per second. Picture that, an object carrying more mass than the Sun, 20 kilometers across, completing 700 full rotations every second. The surface at the equator moves at a significant fraction of the speed of light. And it holds together, because the same extreme density that creates lethal tidal gradients outward also creates a surface gravity roughly 200 billion times Earth's. Drop a marshmallow from 1 meter above that surface, and it impacts with the energy of a small nuclear weapon. That surface gravity is the tidal gradient principle turned inward. The same physics now operating as the binding force rather than the destructive one. The conceptual spine works in both directions. The discovery earned Anthony Hewish, Bell Burnell's doctoral supervisor, the 1974 Nobel Prize in Physics. Bell Burnell herself was not included, a decision that remains one of the most debated omissions in Nobel history. The scientific community has since widely recognized that the observational discovery was fundamentally hers. But the tidal gradient does not stop at the surface. Inside a neutron star, it sculpts some of the strangest matter known to physics. The outer crust is iron, the same element circulating in your bloodstream, but compressed into a crystal lattice 10 billion times denser than steel. A few hundred meters deeper, the nuclei pack so tightly they begin to deform. They are no longer spheres. The competition between nuclear forces trying to maintain their shape and gravitational pressure crushing them inward creates structures that nuclear physicists call, without any irony, nuclear pasta. At moderate depths, nuclei flatten into sheets, lasagna. Deeper, they stretch into tubes, spaghetti. Deeper still, the tubes merge into slabs with cylindrical holes running through them, anti-spaghetti. Bubble phases. These are not playful nicknames for public outreach. These are the terms used in published research papers because the geometries genuinely resemble Italian food. Nuclear pasta may be the strongest material in the universe. Simulations suggest it withstands shearing forces up to 10 billion times greater than steel. And it exists because of tidal gradients at the nuclear scale. Gravitational pressure varies steeply across even a few centimeters inside the star, deforming nuclear matter into configurations that exist nowhere else in nature. Below the pasta layer, individual nuclei dissolve entirely. Neutrons flow as a superfluid, a quantum state of matter with zero viscosity. Stir it and remove the spoon, and it spins forever. This superfluid carries angular momentum in quantized vortices, tiny quantum tornadoes, each carrying exactly 1 unit of circulation. A typical neutron star interior contains roughly 10 quintillion of these vortices threading through its core. This interior explains one of the most dramatic observed pulsar behaviors, glitches. Occasionally, a pulsar's rotation rate suddenly jumps, speeding up by a measurable amount in less than a minute. As a pulsar gradually slows from electromagnetic braking, the solid crust decelerates. But the interior superfluid does not. Zero viscosity means it retains its original spin. Stress builds between crust and core until the vortices suddenly unpin from the crystal lattice, transferring angular momentum to the crust in a single lurch. The star speeds up. A neutron star earthquake, except instead of releasing tectonic stress, it releases rotational stress between 2 phases of matter that exist nowhere else. Observing these glitches from Earth is one of the only methods available for probing what lies inside. Some neutron stars carry magnetic fields 1,000 trillion times stronger than Earth's. These magnetars occasionally release flares of staggering power. On December 27, 2004, a magnetar designated SGR 1806-20, located 50,000 light-years away on the opposite side of the galaxy, released a burst so intense it measurably compressed Earth's magnetosphere and ionized the upper atmosphere. For 1/10 of a second, a dead star halfway across the Milky Way outshone every other gamma-ray source in the sky. The energy released in that fraction of a second exceeded what the Sun produces in 250,000 years. And when 2 neutron stars spiral into each other, an event now directly confirmed by gravitational wave detectors, the tidal gradient reaches its most extreme expression. Each star tidally disrupts the other in the final milliseconds before merger. The collision forges heavy elements through rapid neutron capture, gold, platinum, uranium, created in quantities measured in planetary masses. In August 2017, LIGO and Virgo caught gravitational waves from such a merger 130 million light-years away, while telescopes across the electromagnetic spectrum watched the resulting kilonova unfold in real time. That single observation confirmed what had been debated for decades. Neutron star mergers are a primary source of the heaviest elements in the periodic table. The gold in any ring on any finger on Earth was almost certainly forged in precisely this type of cataclysm billions of years before the solar system existed. Return now to the opening scenario, a rogue neutron star drifting toward Earth. Every stage of the destruction traces to a single principle: disruption of outer planets, tidal gradients at solar system scale; sloshing of oceans, tidal gradients at planetary scale; stretching and disintegration of the planet itself, tidal gradients overcoming self-gravity. And inside the neutron star, those same gradients turned inward create nuclear pasta, superfluid vortices, pulsar glitches, and magnetic fields of incomprehensible intensity. One principle: nuclear scales to astronomical ones, explaining all of it. The probability of this actually happening is vanishingly small. The nearest known neutron star sits roughly 400 light-years away. Even 1 billion wandering neutron stars in the galaxy translates to enormous average separations. The chance of one passing close enough to threaten Earth within the next several billion years is effectively zero. Asteroid impacts, supervolcanoes, and the Sun's own expansion into a red giant are each billions of times more likely to matter first. But the physics is not hypothetical. Tidal disruption events, stars torn apart by supermassive black holes, are observed by space telescopes several times per year. The Roche limit shaped Saturn's rings from moons that drifted too close. Tidal heating keeps Jupiter's moon Io volcanically active, the same gradient principle at gentler scale, generating enough internal friction to melt its interior. Every ring system, every tidally locked moon, every disrupted star trailing plasma around a black hole, all governed by the same tidal gradient. And here is what stays with you. Every atom in your body was forged inside a star, but the heaviest of those atoms, the iodine in your thyroid, the traces of gold in your bloodstream, the uranium decaying quietly in the granite beneath your feet, those were not made in ordinary stellar furnaces. They were forged in the moment when two neutron stars, each carrying the tidal legacy of a collapsed giant, spiraled together and tore each other apart. The temperatures reached billions of degrees, the destruction was total, and from that cataclysm came the material complexity that eventually permitted chemistry, then biology, then a species capable of looking up at the night sky and reconstructing the entire violent sequence from first principles. Tidal gradients are not merely a force of destruction, they are a sculptor. They shred worlds and forge elements. They shape ring systems and trigger starquakes. They are gravity at its sharpest edge, and everything they touch, they transform. The universe built you from its most violent moments, and gave you the capacity to understand exactly how. Like if this was interesting, hit the subscribe for more, and turn that notification bell on.